Okay, welcome everybody to another Ken seminar. Today we've got Xin Wang, who is a PhD student here at the University of Illinois, specifically with the Sustainability and Resilient Infrastructure Systems program within the CEE department. He's working under the oversight and advising of Professor Yang. His research interests include the development of mathematical models and the optimization methods for design and management of intermodal transportation systems. And today he's going to talk to us a little bit about biofuel supply chains. So please join me in welcoming Xin.
Thank you. And hello, everyone. I really appreciate this opportunity to present in the Ken seminar series. My name is Xin Wang, and today I'm going to present my recent topic, Coping with Uncertainties in Biofuel Supply Chain Design, a Continuum Approximation Approach. And this is a joint work with Professor Lim and Professor Yang. Okay, first I will briefly introduce some outlines here. The background includes the biofuel industry, food and energy debates, and also some uncertainties. Then I will go through our modeling framework, and then we conduct numerical experiments to test the performance of the algorithm and also to show some managerial insights. And then we introduce our interactive gaming software related to this problem, which we collect the field data, and actually we implement this software as the education platform in university high school. And finally, I will conclude and discuss some future directions. Okay, so as we all know, the biofuel industry is developed very fast in recent decades. The biofuel or the bioethanol is developed for coping with the energy security issue and also to reduce the greenhouse gas emissions. Currently, the biofuel is widely used in US, especially in the Midwest. And currently in the market, we can see the E10 and E85, which is the bioethanol is blended with gasoline at a certain ratio. So for example, E10 is 10% ethanol plus 90% of gasoline, which can be used in most current vehicles. And for the E85, which is 55% of ethanol plus 15% of gasoline, can be used in most a new developed model, which calls the flex fuel vehicles. So the biofuel can be converted from our edible crops such as the sugarcane, corn, as well as the cellulosic biomasses such as the crop residues, switchgrass, and so on. Now, we call the first one converted from the edible crops as the first generation, and also the cellulosic biomass, we call it the second generation. Due to a series of advantages of the biofuel energy, actually the government set a series of mandates and regulations to boost the development of the biofuel industry in the following decades. We can see in 2022, the government is mandated to 36 billion gallons per year. And also, over 80% of this increase must come from the second generation. Actually, as the development of the biofuel industry, people begin to raise some concerns about, there are some debates about the food and energy. So for example, as the first generation of the biofuel, people use corn to create it, right? So people may argue about if it will reduce the food supply, the increase of food price, and also about the social welfare issues. And also, for both the first and second generation biofuels, the farmer may choose to grow the bio crops, for example, the switchgrass or something. So there are some problems concerning about the farmland use problem. And also, people also raise concerns about the market efficiency issues. That's because if the government subsidize or provide support to the biofuel industry development, will that be affecting the whole market equilibrium? So in short, there is a land use competition between the food and energy, because the total agricultural farmland resources is limited. we need to choose either to eat our food or burn our food. To take a detailed look at our competition, here we can see the most critical part in this competition is farmer, because farmers need to make their decision to how to use their land. So for example, there are food markets and the local crop elevators. So the farmer can grow edible crops such as corn and sell it to the local crop elevator. The price is, for example, the corn price will satisfy a kind of inverse demand function because it reflects the supply and demand relationship. On the other hand, the farmer can also sell it to the energy market. The biofuel firm will build a lot of biorefineries. The farmer can ship their biomass to the biorefineries at contract prices. Then the biofuel firm will collect this biomass and convert it to bioethanol, then sell it to the upper level oil companies where the bioethanol is blended with the gasoline. The ethanol price is similar to the corn price or the crop price. It also satisfies a kind of inverse demand function, but different from the crop price. If we stand at the biofuel firm, we focus on this point. The biofuel firm need to make kind of two decisions. One is to where to build the biorefinery. Another thing is to how to set the contract price with the farmers. And also notice that there are a lot of farmers, and most of them make decisions independently. So actually, you can see they form a bi-level problem, the Stackelberg competition, where the biofuel firm takes the lead and all farmers as a follower, and simultaneously they compete in a Nash competition. So for the biofuel firm to make good decisions, they also need to consider a lot of uncertainties. For example, we know the crop yield is varying over years. On the right, we can see the figure. This is just a statistics of the corn yield in Illinois from 1990 to 2013. We can see it really varies a lot. There are some factors which affect the corn yield or the crop yield. First, soil conditions, such as water, fertilizations, and also another important factor is the weather. So for example, this year the weather is very cold. Maybe next year the weather is very hot. And depending on the weather, the corn or the crop yield are also varying. So we can see due to some common factors or joint factors such as weather, the yield often shows some spatial correlationship. That means, for example, if Illinois, this year Illinois is very cold, then the yield in Illinois is very small, very low. Maybe in Indiana, the yield is also very low because of the weather is very cold there. But for Texas, maybe the weather is not that cold, so the yield is the distance will play a role here to affect their correlations. We can see due to the uncertainties of the yield, the total crop supply may change. And due to the inverse demand function, we can see the crop prices are also affected by these variations. So all of these factors will jointly affect the biofuel firm's decisions. So on the other hand, we can see there are some uncertainties related to the reliability of the service provided by the biofuel firm. We typically assume once we build the refinery, it's always there. But the truth is that there are some natural or human factors which will lead to the disruptions of such kind of facilities. For example, tornadoes, floods, the water supply shortage, and so on. Once such kind of disruptions has happened, there will be a series of impact here. We can see first, the customer demands are reassigned. You cannot sell your product as the disrupted facilities. And also we can see, since that you choose another refineries, the transportation cost will increase a lot. Because the energy market or the biofuel industry is relatively young compared with the incumbent food market, So it's more vulnerable to this kind of disruption or the reliability issues. For example, here consider this is a farmland region, and the biofuel firm has built a lot of refineries, and the farmers always choose to the nearest one, just like this. Once the refinery is disrupted, we can see the farmer will choose the next nearest one, which is open, and the transportation cost is increased. If two of these refineries are disrupted, you can see the farmer can have to choose the next working facility, so which means the transportation costs increase further. So we can see such kind of uncertainties is twisted with the competition, and it has a profound impact on the decisions of both the biofuel firm and the farmers. The biofuel firm has already built refineries and sets the biocrop price. Then there are food markets, and the food market price is given. The farmers will make decisions based on these two markets, and to maximize their profit, they may choose a part of land to grow the biocrops, or maybe choose a part of land to grow the food crop. Then they will pay some transportation costs to the local crop elevators or the refineries. And then collecting the biomass from the farmers, the biofuel firm will sell it to upper energy market at the bioethanol price. So we can see as the yield is, there are uncertainties in the yield. The total biocrop flow and the food crop flow is stochastic or kind of random. And then these uncertainties will have an impact. The biocrop flow will have an impact on the bioethanol price, and the food crop flow will have an impact on the food market price. And also, if the refinery is disrupted, the shipping cost will increase. So we can see these factors will affect the biofuel firm's profit, and these factors will affect the farmer's profit. The problem becomes very complicated and twisted. Currently, most of the typical network models cannot handle such, even formulate such problem. So to this end, we raise our research question: how can we cope with such uncertainties in the biofuel supply chain design? Just as I mentioned, typical network model cannot handle such kind of complex problem. So we address it in a different way. Typical discrete model the modeling demand and the facility locations in discrete points, which is very accurate. And normally we use integer programming or mixed integer programming to solve this problem and find the best facility location from a set of candidate facility locations. Most of the problem are NP hard and very hard to solve or get reasonable solutions in a certain computing time. On the other hand, we have continuous approximation model, which is developed for coping with the large-scale facility location problem and widely applied in this logistic area. So the input and output are different from the typical discrete network models. The demand now we can see is modeled as a continuous density functions. And also the facility locations are also modeled as density functions. Based on this conversion, most of the time we can convert the optimization problem into finding the derivative of these objective functions. Most of the time we can get closed form or good analytical solutions. So for the facility location problem, let's see how the continuum approximation approach can be used here. For example, consider there's a refinery located in X, and it covers a serviced area. We use A to represent the total size. Then we can see the radius can be calculated in this way. In continuum approximation model, we assume the farmers are uniformly distributed in this region. And then, if we randomly pick up a farmer, what's the distance we want to know from this farmer to the refinery? In fact, if we randomly pick it, the distance is a random variable. We can easily get the distribution function for this distance. So our framework, I will introduce our framework in this flow. First, we will use the mentioned continuum approximation model to formulate a baseline model where we only consider the competitions. The competition is modeled as Stackelberg-Nash competition, and we solve this problem use some functional optimization method. Based on this building block, we extend our model to coping with the uncertainties, including the yield and refinery disruptions. Then we conduct numerical analysis to show the performance of our algorithm and generate further managerial insights. So first, let's see the baseline model. So to formulate the problem, let's first focus on what's the farmer's profit. Consider there are two markets. One is food market, one is the energy market. This notation is here just to show the flow. So we use the price minus the total transportation cost as the profit. It is intuitive that the farmers will choose the energy market or to grow bio crops if they can get higher profit in the energy market. However, in continuum approximation model, this profit is not a deterministic variable, but a random variable because the distance is random. Now, with the development of the distribution function, we can see this A represents the surface area of a refinery. So we can see from the continuum approximation model, some farmers have a shorter distance to the refinery, some farmers have longer distance to the refinery. We kind of calculate the average land use for a local neighborhood. So we can calculate the probability that the energy market profit is higher than the food market profit as a decision variable to the whole farmer's decisions. So as we know, the biofuel firm will take the lead. And this is a bi-level optimization problem. I will skip some mathematical details to just show the structure of this bi-level problem. The first objective is biofuel firm's profit. And the second, farmer's decision equilibrium. And also we have the food and energy market equilibrium. You can see an interesting thing here is we need to make decisions on the service area, that is the facility location, and the contract pricing. We want to maximize the total profit of the biofuel firm, but the service area and the pricing are a function. So we need to maximize the functional problem. We use some calculus of variation techniques to solve this one. I will just introduce some interesting phenomena observed in the solution instead of going to the details. We show that actually the problem can be solved in a very easy way. First, we can derive an attractiveness function to each farmer. That means if the farmer has a higher value, higher T value, then the farmer has more attractiveness to the biofuel farm. And then we get a very interesting equilibrium solution. Here, as we mentioned, alpha is the land use for energy, the total proportion of the farmland used for energy. We show it is either 1 or 0. So that means there's no intermediate combinations, just all used for food or all used for energy. Based on this result, we developed a very intuitive algorithm. So consider this is a farmland area. We first discretize this farmland to small pieces. We call it cell. And then we list all the cells in one dimension. Then, since we can calculate the attractiveness, we sort all the farmers based on the order of the attractiveness function in the descending order. So for each cell in this farmland region, we have a corresponding cell in this one-dimensional axis. We calculate cumulative yield for all the cells. And then we can draw another curve, which we call the cumulative yield curve. So starting from 0 to a certain point. If there are solutions, we can show there will be intersections, and the intersection will be the equilibrium of the solution. So that means if a farmer is picked up by the biofuel firm, then all the farmers with higher attractiveness function will also be picked up. So based on this building block, we extend to incorporating the uncertainties based on the yield variation and the refinery disruptions. So at first, we model the yield uncertainties as its average plus a error term. We make some assumptions on the error term. First, we assume that expectation is 0. And we assume the standard deviation is proportional to the yield. And to model the spatial correlation, we consider a Gaussian random field. Here, the rho indicates the weakness of their connections. So if we can see if the two farmland locations live farther, we can see their correlationship will be lower. Interestingly, we observe in our final objective function, only one term is important. That is the yield price joint uncertainties. In terms of the refinery disruptions uncertainty, our existing work has shown that we only need to modify this distribution function by a factor. To formulate this problem, we make assumption that all the farmers make their land use decisions at the beginning of the year. For example, they sign contract and they have already made decisions to grow the biomass. Instead of after they harvest the corn or the biomass, then they choose to sell it to either food market or energy market. Based on this assumption, this whole problem is converted to a maximization problem of the expectation instead of a stochastic problem. So we can see this is I will skip the math details about this problem just to show the structure. It's very similar to the baseline model, but only some terms are modified. Then there are some interesting observations to the solution. First, we can see in the uncertainty case, it's not pure 0 or 1. There are some transition regions. And also, we can see if a farmland, the yield has higher uncertainty or the disruption failure probability is high, then it indicates it has lower attractiveness to the biofuel farm. So let's use some numerical examples to show this algorithm. First, we conduct a hypothetical numerical test based on a unit square farmland region. Consider there are two food markets, which is located in 0.2, 0.2, and 0.7, 0.7. Here is the result. We use white to represent the biofuel, the land use for biofuel, and the gray to represent the land use for food. We can see if there's no uncertainty and all parameters are homogeneous, then the biofuel firm will choose to build refineries relatively far away to the food market. And if there are uncertainties, we can see the farmland use is a little bit different to this case without uncertainties. There are some transition regions. And the total number of biofuel refineries will go down. If we consider a heterogeneous case, that means the parameters are varying over space. For example, the horizontal axis indicates the total yield goes down, and the vertical axis indicates the fixed cost, refinery fixed cost, going down in this way, going up in this way. Compare with this scenario with a homogeneous setting, we can see in heterogeneous problem, the density or the land use proportions a little bit twisted. The biofuel farm is more, will choose more farmers with lower fixed cost and higher yield. So to see the parameter sensitivities, we can see the first question is, what's the discretization resolution we should choose? How many cells is good for our analysis? From this group's, the case 1, we can see as the increase of the discretization rate from 10 to the power of 4 to 10 to the power of 8, the results of the problem are quite similar, especially from 10 to the power of 6 to 10 to the power of 8. The change is very small, less than 1%. So in all the following analysis, we will fix 10 to the power of 6 as the resolution. And then we evaluate how the uncertainties will affect this result. Here, this one means the yield and the price drawing uncertainty, and Q means the refinery disruption failure probability. As this uncertainty increases, we can see the total biofuel profit goes down. Number of refineries goes down. On the contrary, the biofuel firm has to increase the collective price. And the total food supply goes up. So that means the uncertainties have a very negative effect on the biofuel industry. Consider the heterogeneity, the space heterogeneity of these parameters. We can see it's very insensitive. This is because our problem has already addressed this heterogeneity issues in our modeling. Then we conduct a Midwest case study to show some managerial insights. First, we assume that the Midwest region contains 8 states, and all the food markets are located in each state as a city with the highest population. And then we get the data of the annual yield in this Midwest region based on a county level. So here is the result. This figure shows the land use proportions for energy. If it is darker, that means this region. There are only 0 and 1 for the deterministic case. Then we can see it is either all used for energy, which is dark here, and all for food, which is white here. In the stochastic case, we can see the result is a little bit different. The biofuel region is a little bit dispersed based on this uncertainty. And also, previously, the low yield region is considered by the biofuel firm because in our problem settings, low yield has a relatively lower uncertainties. Then, to consider the refinery density was the optimum refinery numbers and where to build it, we can see in the deterministic case, they built 15. But when there are uncertainties, the total number of refineries goes to 12. And also, it's a little bit dispersed. We also developed an interactive game based on the competition of the land use. So here is a structure. We have a server and a lot of clients where each client can serve as the farmers or the biofuel farm. First, we establish a map, which, for example, we can establish Illinois map and then put it into the server. And then all the players, they either play farmers or play the biofuel company, and they compete with each other. So here, I just want to show the demo. So first, we create some map, just as a typical computer game. We set where's the food market, where's the biorefinery, and also where's the farmland. And then after we created this map, we set how many players in this game. Typically, we have only one biofuel company and a lot of farmers. Then first, the biofuel company, as a player, they will log into this game. And all the farmers also log into the game. The biofuel company first sets the price, collecting price, and where to build the refinery. What's wrong? Sorry for this.
We're going to switch
This one?
Yeah.
It's okay now, right?
As good as I'm going to get it.
Okay. Yeah. So just as we still see the game, and the farmers make their land use decisions on the biofuel farm or choose to sell to food market. They just repeat this procedure for each year represent one round. And this window will show what's their profit, history of their profit, and history of their decisions. Yeah, game over, just a full illustration. Sorry. Yeah, and finally, in conclusion, we can see that if there are uncertainties, the land use patterns is more like exclusive patterns. They either grow food or energy. If there are uncertainties, then we can see the energy market is more vulnerable. And the result shows that the region with lower yield may be more preferred by the biofuel firm because it has lower uncertainties. Also, the biofuel firm needs to build more refineries to conquer the uncertainties issues. So in the future, we consider to expand our work in the following directions. First, we can consider the perennial belt crops in the multi-year decision problem. And then we can also investigate the farmer's decision problem by considering the risk aversion issues. Compared with the biofuel industry, the farmers is more risk aversion. And then we can also consider the government policy, what's the impact on the competition, such as tax, subsidy, or the mandates they set. Okay, thank you. Any problems? Okay.
How do you account for the different modes of travel or transportation, like rail? Or...
Yeah, here we just make a simple assumptions that the total transportation cost is proportional to the distance. Yeah, thank you.
So you said one of the assumptions was that a specific field would be allocated for biofuel use or non-biofuel. How significantly would results be affected if the decision was made later, as you mentioned?
Yeah, that's a very good question. And currently, this is our model settings because if we consider the farmer's decisions in the end, then that is a totally stochastic programming problem. We are still working on this as our extension directions, but it's not incorporated in the current model. Currently, we assume the farmers make decisions at the beginning of the year. For example, after they sign contract with a biofuel farm, they already decide they will grow, for example, sugarcane or some other cellulosic biomass and sell it to the biofuel farm. So that's a typical phenomenon in first generation biofuel because they grow corn and then they sell it to either food market or the energy market. But for the second generation, typically they do not sell the biomass to food market, right? Because it's not edible crop. They typically fix their decision at first to grow it. So there are different type of decision problems associated with these generations. So any further concerns? Thank you.
Thank you.
Yeah, thank you.